Okay, now we're going to go ahead and take a look at some shortcuts to taking derivatives. So we've learned how to find a derivative using the limit of the difference quotient, and if we observe some patterns, we can really shorten up that process quite a bit. So first of all, we know that the derivative is the slope. So if we look at a constant function like y equals 0, y equals 1, y equals 2, the derivative has to be 0, because if you graph that, it's a horizontal line that always has a slope of 0. Okay, so we found the derivative before of x squared. We can use the limit of the difference quotient, simplify it down, and we end up with 2x. We could take the derivative of x cubed in the same way. If you remember back to Pascal's triangle, you can use that to help yourself when expanding polynomials of higher degree. And we can cancel, and we end up with 3x squared. If we take the derivative of x to the fourth, we can use Pascal's triangle again, and we get 4x cubed. And hopefully you're seeing some sort of a pattern here. We get 2x, 3x squared, 4x cubed. If we went on, we'd get 5x to the fourth, 6x to the fifth. So in general, the derivative of x raised to any number n is n times x to the n minus 1, meaning bring the exponent down and reduce the exponent by 1. So derivative of x to the 8th would be 8x to the 7th. We call that the power rule. Our constant multiple rule. So if you have the derivative of a constant times a function, it's just the constant times the derivative of the function. So here it is in a more general form. A constant times x to the n would be the constant times n times x to the n minus 1. So that's us using the constant multiple rule along with the power rule. So the derivative of 7x to the fifth, we bring the 5 down and reduce the exponent to 4. 7 times 5 is 35. We have our sum and difference rules. So if you take the derivative of the sum of two functions, you can just take the derivative of each function independently. If we think to the difference quotient, it would look something like this, and we could split that into the sum of two separate limits, each of which is the derivative of one of the functions. And by that same sort of reasoning, we have our difference rule. So if we're taking the derivative of x to the fourth plus 12x, you can just deal with each piece by itself. The derivative of x to the fourth is 4x cubed, derivative of 12x is 12, and we're done. Derivative of x to the fourth is 4x cubed, derivative of negative 2x squared is negative 4x, and the derivative of a constant is 0. We want to find horizontal tangents, so we can find an equation that will give us the slope, and we know that we have a horizontal tangent when the slope is equal to 0. So we take our derivative, we set the derivative equal to 0, and we can solve for x. We can factor out a 4x, or cancel out a 4, factor out an x, factor x squared minus 1, and we find there are three values of x where this equals 0, 0, negative 1, and positive 1. If we plug those back into the original, we can find the y values where these occur, y equals 2, y equals 1, and also y equals 1. So really we just have two horizontal tangent lines because y equals 1 is the tangent at both x is 1 and negative 1. There's the function, equals 2. We can see that those are clearly the horizontal tangents. There's the derivative, and we can realize that, well, if there's a horizontal tangent at negative 1, 2, and 1, the derivative is 0 at both of those points, so it makes sense that the derivative goes through negative 1, 0, and 1 along the x-axis. And you can look at the slope. We initially have a negative slope until we get to 1, so the derivative is negative. From negative 1 to 0, the slope is positive, so we graph positive y values. From 0 to 1, the slope is negative, so we dip back down below the x-axis. And then for all values of x greater than 1, we have a positive slope.